My name is Marco Misenta. I'm part of the technical support and training team at CMG, and in this video I will be talking about halite precipitation modeling in CO2 storage using CMG's compositional simulator GEM. Injection of CO2 in aquifers can lead to precipitation of salt. We know that this is a consequence of the process of water vaporization, which happens as we inject gas into a water-saturated region. Part or the whole amount of water in some areas near the well can be vaporized, which leads to a local increase in salinity and the potential for salt to precipitate, reduce porosity, affect permeability, and eventually affecting the well injectivity itself. A typical process that we can expect is the precipitation of sodium chloride, halite, in the proximity of the well during CO2 injection in an aquifer. So we start with the GEM model, base GEM model for CCS in aquifer. The aquifer parameters are reported here in terms of pressure, temperature, porosity, and permeability. This is a synthetic box model with an injector well in the middle. Here we have also a cross-sectional view of the injector well. The brine properties in terms of density, 1095 kilograms per cubic meter, and then sodium and chloride concentrations, original concentrations are known, and they are respectively equal to 60,000 and 120,000 ppm, and I will show you later how to input this data into the model. The well constraints, so the well is injecting pure CO2 with a constant injection rate of 100,000 standard cubic meter a day. The well is injected for a month, after which it is shut. So starting from the base CCS model, what do we need to enable to allow the modeling of halite precipitation? So first of all, the water vaporization process needs to be added on to model the dry out effect during gas injection. Then we need geochemistry. Geochemistry models a wide variety of reactions in the aqueous phase as well as in the mineral phase, and this can be combined, mixed and matched in many models. But in this case we really only need one reaction, which is the halite reaction. Halite equal to Na plus Cl minus. This reaction is modeled as a kinetic rate dependent reaction that requires the input of these parameters: the halite reactive surface area, the halite activation energy, and the log time of the reaction rate. The data that we see here were taken from the default database linked into GEM, which is the Wallery database referenced at the bottom. Other databases can be linked into GEM as well, and optionally the user can override any of this data with some laboratory measured data. And then for the impact on flow due to mineral precipitation, we will have two options. One is the porosity change due to mineral concentration changes. This is a default option in GEM as soon as geochemistry is enabled. And then optionally the user can activate the option for calculating the residual resistance factor, which is calculated on a phase-by-phase basis by several options. This residual resistance factor is a scaling factor for the effective permeability of each phase. So the options available are the Kozeny-Karman model, the power law model, or alternatively the user can input a porosity versus permeability table directly into the dataset. In this example we are using the power law. So let's see how this case was set up. Looking at the builder interface, we can go to the process wizard section of builder and bring up the carbon capture and storage wizard. In this wizard we can activate various options. So we have the solubility in water is already enabled, and then we additionally added the geochemistry option by checking this box, and the water vaporization option. In the next section we can input the geochemistry data. So here is where we select the reactions that we need. So amongst hundreds of reactions available, we pick just one reaction here, which is the halite reaction from this drop-down list. The halite reaction comes in with its own values of surface area, activation energy, and reaction rate. As we saw in the presentation, this can be overwritten if needed, or another database could be activated to bring in alternative parameters for this reaction. We go then to the next step, where we input the original ionic concentration. So the 60,000 ppm for Na plus and 120,000 ppm for Cl minus will be input here. We also need to specify the mineral original volume fraction, which is assumed to be 0. No mineral in a solid form is originally present in the model. So once we run the model, we can visualize the results into the results interface. This is the plateau of injection rate for a month. The CO2 plume, we modeled the solution in water, so we can see the CO2 plume towards the end of injection evolving in the model. And then in terms of mineral activity, we can calculate the mineral density from the output. So the mineral density here is of course the halite density, as that's the only mineral that we are modeling in this case. So the mineral density will be null at time 0. And then I'm showing the map of the mineral density at the end of the injection time, which shows that the mineral has indeed precipitated and accumulated in the near wellbore region. We can also track the other processes that happen simultaneously. The important one, as we said, is the water saturation change. So the water saturation has changed from original value of 100% to down to 0.01 fraction. So a lot of water has vaporized here, leading to precipitation of salt. We can also always check the output for the gas mole fraction H2O to see the percentage of H2O that has actually vaporized in the model. Additional output available is the porosity change due to mineral precipitation. As we saw in the presentation, we can output the calculation of what fraction of the porosity change is due to the impact of the mineral change, irrespective of the pressure effect. So we can see that originally, again here, if I go to the original time step, the porosity change is 0 due to mineral, and here I'm showing the porosity change at the end of the injection time, where the conclusion here is that most of the porosity change due to mineral happens, of course, in the near wellbore region, consistent with what we saw with the mineral density plot. And finally, we can also have a look at the gas resistance factor. For instance, this is the gas resistance factor at time 0. This is 1 everywhere in the model, even in proximity of the well, when there is no precipitation happening. As soon as we switch to the time step where we see precipitation further down the line, we can see the gas resistance factor is now larger than 1, and this will be the scaling factor used for the effective permeability of gas. So thank you very much for your attention during this video.